Okay. We also have octane X. Remember, we integrate this thing. Okay, what do we get is integrate 0. Let's use 0 to x whatever this thing, t squared. So if you expand use geometric series, then this is actually 0 to x 1 minus t squared plus t4 minus t6, etc., etc. Now assume that here we can termwise integration. So this you fundamental theorem of calculus. Okay, so you get a t minus t cube, etc., etc. Fundamental theorem of calculus 0 to x, and then termwise. So this will be x minus x cube over 3 plus x5 over 5, etc., etc. So finally, we have this power series representation octane x, which will be x minus x cube plus x. It's alternating, okay? They are both odd powers over odd numbers, etc., etc. This will be use sigma notation, x to the power 2n, let's suppose minus 1, 2n minus 1, x to the power n, let's use n plus 1, n from 0 to infinity. Okay, so this we get the power series representation of octane. Okay, let's see some examples. Now, find power series representations of. Okay, example. Find power series representations. Find a power series. Power series representation for the function fx equals octane x over 3. Okay, what we do is we manipulated the octane, the power series of octane. So we let x be x over 3. Okay, so from the equation power series representation of octane. So we replace x by x by x over 3. Then you get octane x over 3. This will be, now remember we just replace x by x over 3. So we use sigma notation to avoid any complicated algebra. -1 to the power n. So it's x over 3 to the power 2n plus 3, 2n plus 1 over 2n plus 1. And then simplify a little bit. So this will be n from 0 to infinity, -1 to the power n times, now denominator is 3 to the power 2n plus 1 times 2n plus 1. Now x to the power 2n plus 1. Then we are done. Very easy. We just do substitution. And then we use algebra to simplify a little bit. Okay. More examples.
Qn plus 1.
Okay. Okay. More examples. Here we need to be careful. Here x can be its value. What is when x converges, when x diverges? Now here x can be 1. Alternating. X cannot be -1. X cannot be -1. X can be 1. When we write down power series, you need to write down the interval of convergence. So here. We replace x by x over 3. X over 3 is bounded by 1, equal to 1 is also okay. -1 cannot be -1. So here x is bounded by -3 and from above by 3. It can equal to 3. Okay, more examples. Let's see this example.
Why is it 2 inputs?
Okay.
1?
Example. fx to be this example. How do we determine the power series of this thing? Well, remember when we use geometric series? Recall, we have geometric. Now, geometric series. Remember 1 plus x squared plus etc. etc. This is a sigma of powers of x power. So this is a 1 over 1 minus x. Okay. So the first term over 1 minus common ratio. Okay. So the common ratio R is common ratio. Common ratio. Now, if you take the ratio of adjacent terms to any adjacent terms, okay, then you get the value. The common ratio. Its ratio is actually x. Okay. For any adjacent terms, you get x. It's the ratio. So it's common for every terms. Okay, so it's common ratio. The first term is actually a equal to 1. Okay, you substitute a by 1, substitute r, the common ratio by x, then you get this thing. So here we assume the common ratio r is bounded by 1. I.e., here x is bounded by, its opposite value bounded by 1, i.e., x is from -1 to 1. Okay, so you see the right side of the geometric series is a polynomial. Okay, the denominator is polynomial. It's a rational function. Now this denominator is degree 1. Now how do we get denominator in degree 2? So here we have 1 plus x. Here we have 1 minus x. Okay, we want 1 plus x in the given example. So if you replace x by negative x, then we get a negative x to the power n from 0 to infinity. Now you get y minus negative x. Okay, this will be 1 plus x. Again, x is bounded from -1 to 1. Okay, now how do we get how do we square the denominator? So here in this case, the example for the geometry series, we get a degree 1 in denominator. Now how do we get a square in denominator? Remember, we have Cauchy rule. Cauchy rule says f over g derivative is g squared f derivative times c over f times g derivative. So if we differentiate use Cauchy rule, actually we square denominator. So this is related. So we want to square denominator. So what we do is we differentiate. So differentiate both sides. Differentiate both sides with respect to the variable x. Then you see the left side is d dx. Now the power series is n from 0 to infinity, x to the -1 to the power n, x to the power n. The right side is d dx, 1 over 1 plus x. Okay. Now we remember in this course we can always switch. Okay, we can always switch in this course. N from 0 to infinity, -1 to the power n. We can switch term-wise differentiate. Now the right side derivative, actually we use power rule and chain rule. Or you use Cauchy rule, you get this result. It's very easy, so we will skip that. How we get that? So the left side, you see, use power rule. Okay. Then what we want is, remember now. So what we want is actually 1 over 1 plus x squared. So we multiply -1, and then we get switch. This we get n from 0 to infinity, negative 1 to the power, now power n minus 1. We multiply negative 1. So n times x to the power n minus 1. Okay, here n start from 0. N start from 0. N times, so the first term n is 0. 0 times anything, we get 0. So we can actually start at n from x to be, n start from 1. Okay. N start from 1. If you write down several terms, so this will be x. The first term when n is 1, then we get 1. The next term is 1 minus x. Sorry, the next is minus 2x. N is 2. And then the next term is 3x squared minus 4x cubed, etc., etc. So it's alternating sum. You know, the degree increases by 1. And then the coefficients actually increase by 1. Coefficients increase by 1. So it's alternating sum. Okay. Then we are done. Okay. Now, how do we find, for instance, how do we find this? Example. How do we find fx to be power series representations of this x cubed? Now we know from the last example that we did is actually degree 2, 1 over 1 plus x to squared. Now to get degree 3, we once again differentiate, okay? And when we use power rule, the degree decreases by 1, okay? Then we actually, you see, differentiate the equation. Let's level the equations. Let's use equation 1. Okay, I may have a trouble with the leveling because here this is locally clear, but okay, so we differentiate both sides of equation 1. Both sides of equation 1. So we get d dx. The right side, we differentiated term-wise. Okay, d dx. Now here, n start from 1 to infinity, 1 to infinity. Now this we get negative 1 to the power n minus 1, n x power n minus 1. So switch, okay. N times d dx. N minus 1. And then you see this, we get the left side we use power rule, okay? So we get a negative 2, okay? To the power, degree decrease by 1. Then we get a degree 3, okay? Negative 3. The right side use power rule, okay? N, now use power rule. The power n minus 1, so factor out the exponent. Then degree decrease by 1, n minus 2. Okay, n minus 2. And then we divide both sides by negative 2. Okay, so it's negative 1/2. Now here, we start from n to be 1. Remember, when n is 1, n minus 1 is actually 1 minus 1 is 0. So we can actually start from n to be 2. Okay, we start from n to be 2. Okay, n times n minus 1, x to the power n minus 2. Okay, then we are done. Then we find the power series representations of our desired functions. Now, of course, you can actually differentiate it, get any higher power. Okay, to get any higher power. Okay. Now, of course, the radius of convergence is actually sometimes if you differentiate or integrate, sometimes you can change the convergence. You have to be careful. So the convergence can change at the boundary. For instance, the convergence changed at the boundary. if you differentiate and integrate it, sometimes the boundary value can change. So here x is bounded by 1 and -1. Here you can use the ratio test. You can use the ratio test to find its radius of convergence and interval of convergence. Okay, be careful.
You have to differentiate.
Okay. Example. Find the power series representations of this fx to be x 4x plus 1. 4x plus 1. Find power series representations of this thing. Okay, remember what we usually do is we use geometric series to expand to get powers. Okay, so the geometric series we get y a over y minus common ratio. Okay, if you compare, so here the denominator that's 1. So try to manipulate. So a, which is a to be x. Now we have 1, so we just write 1. Y minus r. So you minus. So here the remaining term is 4x. So 4x is you write as minus 4x. Okay. So you see a, the first term, choose a to be r, and choose a to be x. What I did, a to be x. The first term is x. Okay. Let's compare the numerator. So you choose a to be x, and then compare denominator. We choose r to be common ratio to be -4x. Okay. So this thing will be, to expand n from 1 to infinity, a times r minus 1. The expansion of geometric series. So this will be n from 1 to infinity. Now a is x, r is -4x to the power n minus 1. Okay. Now this will be expanded thing, n from 1 to infinity, x times -4 to the power n minus 1, x to the power n minus 1. Now this x times n, x to the power n minus 1, so this is x to the power n, -4 to the power n minus 1, n from 1 to infinity. Remember, once we apply geometric series representation, geometric series expansion, then what we require is common ratio should be bounded by 1. In this case, -4x absolute is bounded by 1. So x is bounded, absolute is bounded by a quarter. So x is bounded by a quarter and -1/4. Okay, so this is interval of convergence. Radius of convergence. Radius of convergence is half of the length of the interval. Radius of convergence. Actually, it's very easy to find. It's actually r is, a quarter. It's very easy. Half the length of the interval. Then we are done. Okay, then we are done. More examples. This is example. Okay, fx to be x over 9 plus x squared. Okay, now in general, we will try to use geometric. Okay, compare. Now here x, you see here, is this compared these two fractions, you see a, we can choose a to be x. Okay, now the denominator, we don't have 1, but instead we have the number 9. Okay, now how do we change number 9 to number 1? Okay, what we do is we will factor 9. Okay, factor 9. So this will be x over 9 times 9. Then factor out 9, then you get 1. Now x squared, if factor out 9, you get x squared over 9. Okay, so you see this, if you compare, this is 1 over 9. Okay, x 1 plus x squared over 9. Now 1 over 9 is constant. You multiply a power series by a constant, you again get a power series. So you can compare this thing is, you know, forget this constant 1 over 9 now. Now you compare, you see E correspond to X. Now Y correspond to Y. Now R, negative R correspond to this thing. Okay, so negative R correspond to X squared over 9. So you choose A. So our choice for this problem is A is X. Okay, A is X. A is X. R is negative X squared over 9. So, and then we use power series repetitions. Power series repetitions of summation formula for geometric series. So don't forget this constant 1 over 9. And then the other term we use, the other factor is power series repetitions. So this is actually, we use geometric series. So remember geometric A R to the power n minus 1, n from 1 to infinity. So n from 1 to infinity, A by our choice, A is X. Now here our R is actually X squared over negative 9 to the power n minus 1. Then you do a little algebra. So it's 1 over 9 times n from 1 to infinity. Now X times, you know, it's negative 1 over 9 to the power n minus 1. Now X squared to the power n minus 1. So if you multiply 1 over 9 inside, so it's n from 1 to infinity. Now X times, so it's negative 1 to the power n minus 1. Now 9 to the power n minus 1, but we have another 9. Okay, so it's n minus 1 plus 1, so it's 9 to the power n. Now X, now we have a power X, we have power, you know, power 1, and then plus 1 plus, you know, the other 2 times n minus 1. Okay, so this will be n from 1 to infinity, negative 1 to the power n minus 1 over 9 to the power n, x to the power, you do the algebra. So you got a 2n minus 2 plus 1. So it's 2n minus 1. Okay, the radius of convergence is, so we assume R is less than 1 because we use the summation formula of geometric series. Okay, so here this means negative, substitute R by negative X squared over 9. Also valued by 1. So you get X also value is bounded by 9, X bounded by 3 and negative 3. Then we are done. So the radius of, now radius of convergence equal to half the, you know, R equals half the length of the interval. So half of the length of interval is 3. Okay. You see, the general technique to use power series repetition is we manipulate the geometric series. Okay, we manipulate this geometric series, and then either we expand it, or we differentiate. We can do the algebraic operation like a differentiation, like integration. Okay.
How do you know the final form?
Okay. Now, sometimes we can even use, now this, actually we have 2 terms. The denominator has 2 terms. So we can apply summation formula for geometric series. Now, suppose we have this example, a little more complicated example. We use some other ideas that we learned is the following example. Okay, so fx is 3 over x squared plus x minus 2. Now here the denominator has 3 terms. The denominator has 3 terms. Now, so this thing, the summation formula for geometry series does not apply directly because the denominator has 2 terms, 1 minus r. Okay, 1 minus r. Now, if you still, you know, construct r, you know, then you somehow you need to combine 2 terms. Then once you expand powers of R, you know, then this thing, the algebra will be totally disaster. So we don't do in that manner. So we will try to make it to be 2 terms. The algebra that we do is partial fraction decomposition. Use partial fractions. Partial fractions. Remember partial fractions. Partial fractions. Now let's look at the denominator. So we first factor the denominator. Now this is quadratic. We can easily factor it. It's plus 2 minus 1. Okay, so it's a distinct. So it's a product of two distinct linear factors. In this case, according to the rule of power series of partial fraction decomposition. So what do we write down for the power series for the partial fraction decomposition is a over x plus 2 over plus b over x minus 1. Okay, so this is the we write in this form according to the partial fraction decomposition rules. Okay, for distinct product of distinct linear factors. Okay, and then we determine a and b by algebra. Okay, we determine a and b by algebra. So multiply both sides. So here we use partial fraction. Partial fractions. Now we determine a and b. So multiply both sides by the denominator. Multiply both sides by the denominator. Then you see this left side will get a 3. Then you get a 3 equal to, now cancel denominator. The right side, so distribution, we distribute. So a over x plus 2. Now the factor that we multiplied, this thing is, we factor it. So it's x plus 2, x minus 1. Plus b times x minus 1, x plus 2, x minus 1. Now we clear denominator, cancel denominator. So we get a times x minus 1 plus b x minus 1. Okay, so you can solve by algebra, compare the coefficients of both sides. Okay, or you can also take some special values. So this is x plus 2. You take some special values. For instance, you take x to be 1. Then you get a 3 equal to 0. Now the first a times 0, plus b times 3, which is 0 plus 3b. So this is 3b. So this means b equal to 1. Now how do we get a? We take the second factor that has b to be 0. So we take x to be negative 2. Then we get then this will be take x to be 2, negative 2. Then what we get is 3 equal to a times negative 2 minus 1 plus b times negative 2 plus 2. Negative 2 plus 2 is 0. So this is actually negative 3a plus b times 0. So it's 0. So it's negative 3a. So we get a is actually divided by negative 3. A is negative 1. E is negative 1. So we get the partial fraction decomposition. 3 over x squared plus x minus 2. Partial fraction decomposition. So this will be two factors. A is negative 1 over x plus 2. B is 1. Now you see the denominator is linear factors. Okay, the denominator is linear factors in degree 1. So we can now apply geometric series. Okay, so we can apply geometric series. Okay, so this you can write as negative 1 over 2 factor of 2, 1 plus x over 2. Now the second one you can write as 1 times factor negative 1, then 1 minus x. Okay, now we can use a geometric series. Okay, geometric series. So the first term, okay, the first term, we can use geometric series. Okay, geometric series. Find a common issue. R is a 1 minus r. So A, you can, so it's factor out, so it's A to be 1. This is 1 times negative, you find what R is, N minus 1, N from 1/2, N from 1 to infinity, okay? But then next one we will get, so 1 over 1 minus X. So this will be, first term is 1, common ratio is X, N from 1 to infinity. We already factor out a factor -1. Okay, so then by algebra, so this will be, you'll find, this will be X to the power N minus 1. Now what's the coefficients? So X to the power N minus 1 multiplied by coefficients -1/2 to the power N minus 1. Now we have another -1/2. Okay, so this is minus N from 1 to infinity X to the power N minus 1. Okay, so this is actually, see, this is, so here N from 1 to infinity. Now this is the X N minus 1 to the power, multiply -1, -1/2 to the power N minus N from 1 to infinity X power N minus 1. And then you can count, do the algebra. So N from 1 to infinity, add them together. So X to the power N minus 1. Now the denominator will be -1 to the power N over 2 to the power N minus 1. Okay, so this, we get a power series representations. Okay, so we get a power series representation of the given functions. Okay, so the idea for this problem is we use partial fraction decomposition. This technique, actually we will use this technique to derive. Now this idea is important. We will use this idea to derive the Fibonacci numbers. Okay, we will derive the Fibonacci numbers from this partial fraction decomposition. Later we will use this idea. To derive, to find the general, the explicit formula for the Fibonacci number for Fn, Fibonacci number Fn, the Fibonacci number. Okay, Fibonacci number. Now let's talk about Fibonacci number. Okay, now let's do another example. Okay, this example. Okay, evaluate the indefinite integral as a power series. Okay, so this one. Okay, now the old technique, when we use when we find antiderivative, we use substitution, integration by parts, partial fraction decomposition, etc., trig substitution, etc. Now today we have another technique, i.e., we can expand of the integrand in terms of a power series. Okay, and once we have a power series, to find its antiderivative, we simply use power rule. More or less, we are dealing with, polynomials. Okay, something looks like a polynomial, And a polynomial in general, we can very easily find its antiderivative. So this is actually one of the advantage, the benefit when we expand a function by a power series. Yeah. Now this example, actually, if you try to use substitution, etc., it turns out maybe hard. Okay, maybe hard. Okay, we will not do in that manner. We will not bother to try to find its closed formula. Okay, close the explicit formula in elementary functions. The thing is, for very reasonable functions, for very reasonable functions, sometimes it's possible that, for elementary functions, you cannot even write down the antiderivative in terms of elementary functions. Okay, so the antiderivative exists, but you cannot write down it in terms of elementary functions. However, very often you can write it down in terms of power series. So the power series representation actually gives us more flexibility to find antiderivatives. So let's work out this example. So we use the power series representation of ln. Remember ln, 1 minus t negative. So this is actually t plus t squared over 2 plus t cubed over 3, etc., etc. So this is actually sigma t to the power n over the factor n from 1 to infinity. Now, if you multiply both sides by -1, then you get this ln 1 minus t is negative the thing, t to the power n over n from 1 to infinity. Now, if you divide, so this is valid if t is this is valid if t here t is bounded by 1 and -1, and so it can be -1. It cannot be 1 here. So at the -1, it's alternating series. It converges. At 1, you get the harmonic series. So diverge. So it's converges at -1, diverges at 1. Okay. And then we divide by t. So this ln 1 minus t divided by t. So this you get negative n from 1 to infinity. Now t to the power n divided by 1. So the degree decreases by 1. Use power rule. Okay. So then we get this is a negative n from 1 to infinity t to the power n minus 1 n dt. Okay. Now, as we mentioned, in general we can switch the in this course. I mean, you can switch the order of integration and summation. So this is actually negative summation n from 1 to infinity, integrate 1 over n t to the power n minus 1 dt. You can find its antiderivative. So its antiderivative is increased power by 1 n. Okay, and then this is the t to the power n. Okay. Now, right now, what is the where does the constant go? So you just write down the constant at the end. Okay. So you see, this is negative 1 over n squared Tn, n from 1 to infinity. Let's see. You see what happened? So somehow this is related. This is related with this problem 1 over n squared. Now remember, the sum of 1 over n squared is actually a classical problem, and this problem is somehow related. Okay, is related. Now you see, if you forget the constant c, the series, the power series in t, 1 over n squared t to the power n from 1 to infinity. Now actually the radius, the boundary value, actually, remember the old technique, the series, the original series converges at -1, diverges at 1. So here, this t is valid. It converges if t is 1 and -1. So the convergence is changed at the boundary. It also converges. Okay. It now converges at t equal to 1. i.e., if you do manipulate by differentiate or integrate, sometimes the reader does not change, may not change, but it's possible that the convergence at the boundary changes, i.e., convergence property may differ, may change on the boundary once we manipulate by differentiation or integration. Okay. Okay. Now you see what you see is if this thing, if t opposite 1, as t opposite 1, then you see as t opposite 1, then what you do is this thing t to the power n, this actually approaches 1 over n squared. Somehow this integral is related with 1 over n squared. Now you see this is well known. This is well known. The right side 1 over n squared converges to pi squared over 6. Now n cube, this nobody knows. Open problem. Now can you find something comparison get a similar thing? Okay, similar thing. What is the left side? Actually, there are people study this kind of thing. Unfortunately, we don't have time. Okay, let me just stop here for for the new material today. And now the remaining time, let me give you a quiz. Let's do a quiz.